Okay, so welcome everybody to today's machine learning class. So there's one thing that I really need to rely on from you. So some people told me I'm going way too fast with things. Some people told me it's too easy. Okay, now, the way to make me go faster is that you don't ask questions. The fewer questions you ask, the faster I'll go. The more questions you ask, the slower I'll go. Okay? So, anybody who tells me that I'm going too fast just needs to ask me questions and I'll slow down. Right? Good. The other thing is, I'll ask you guys also questions to make sure that everything's okay. Now, another thing that I got from the forums is I'm putting too many equations on my slides. Okay, so somebody came up with this insanely cool measure of equations per minute. Yes, I'm on the high end there, I'm sorry. It would be very easy for me to reduce that by just skipping details. So, I'm putting a lot of equations there such that afterwards, when you go through this stuff at home, through the slides, which of course all of you will do, right? You actually have the intermediate steps for some of the derivations. So this is meant to help you. So not all the equations that you're seeing on the slides are meant for you to remember. There's no way you can remember one equation per minute. I mean, at least I couldn't, right? So this is why there are slides that are green, which are like, this is stuff you really should remember. And there's some other slides that are maybe yellow or red, which are things you should know, but at least you should be able to derive the stuff on your own, right? So, now, to make things really easy, we'll start with Gaussians today, and we'll have a little bit of fun with Gaussians and then get to Gaussian process regression. And so this is a little bit of a switch back from the theory that we did in last week. So today we'll look at some algorithms that you can use specifically to solve certain classification regression problems. The other thing is, some people ask, why do I need to know all of this? So, in case you have that doubt, raise your hand and ask when I talk about this stuff. So, if you can avoid postponing your questions until until the forums, it'll be a lot more useful for everybody because quite often somebody else may have the same question. To help with that a little bit, I'll stick around after the class for about half an hour outside the lecture theater. So this will be part of my office hours, and I'll try doing that whenever I teach a class. Okay? So that helps you probably also a little bit because then the questions will be more fresh in your mind. I think at some point people will kick us out and complain that we're making a lot of noise outside and people congregating where they shouldn't. But this seems to be something that, well, let's try and see whether that helps you. Okay, good. So ask questions to slow me down. Good. So we're going to start with Gaussians. So okay, this banknote doesn't exist anymore, but this was a really useful thing when I was in high school because it had the equation for the normal distribution on the banknote. So when I was in high school, and of course, we would do Gaussians, and everybody would pull it out, and nobody got this equation wrong. And if you were to squint really hard, you'd see the math for it, right? So everybody has seen a Gaussian before, right? Here they are, fatter and skinnier and with different means. If you open Wikipedia, you'll see exactly that picture. So thank you, Wikipedia. So in 2 dimensions, the things look exactly the same, except that, well, now you can have and so this is done if you use something like Surf-C or contour plots on Octave, or MATLAB will give you a similar picture. Here is, well, a Gaussian that is now not axis aligned. If you squint, you see it's a little bit shifted, and that's what it looks like in 2 dimensions. Nothing special. Here are a couple of samples in 2 dimensions, and what you already see here is, well, there are like 2 main directions in that data, right? There's like there's something going on here. That's the direction of really largest variation. There's something going on there. And as we'll see afterwards, these are what's called the principal components. So the principal components are nothing else but just the eigenvectors in eigenvalue pairs of, you know, a matrix. So if you have done any linear algebra, you'll know what they are. They just have a funny name in statistics, and that's about it. Well, the other nice thing is that if you have principal components, if you look at that data, then maybe, you know, if I were to squish it here, then, well, you know, you'd get something that reasonably well gives you a caricature of the data, so this is fine. In 3 dimensions it works the same, but it just doesn't visualize so well. So, now, here's the math, and this is an equation you should remember. So, because those banknotes are by now not in production anymore, they're just the euro rather than Deutschmark, right? So, this is P of x for, you know, scalars. It's just 1 over square root 2 pi sigma squared, and we'll actually get to where this 2 pi comes from in a moment. We'll see that. And then, you know, here's just the e to the minus 1 over 2 sigma squared x minus mu, oops, typo, squared, right? So Gaussian. Who has not seen a Gaussian before? Okay, good. I've heard that some of you haven't seen the Gaussian in d dimensions yet. Okay, so here it is. And let's first just, you know, look at the equation, and then we'll grok it and see why this is actually the same thing as what happened before. So P of x is 1 over 2 pi raised to the minus d over 2. So, you know, here we have 2 pi to the minus 1/2. In the dimensions, it's, you know, basically, you know, the dimensional product. Now, this is the determinant of a matrix. Remember, the determinant of a matrix is the product of all the eigenvalues. 1 over that. And then here we have x minus mu, so it's the same thing as before. And rather than x minus mu squared, we have x minus mu transposed sigma inverse x minus mu. So let's see where this term comes from and where we get this. So everybody has seen an eigenvalue decomposition for a matrix, right? So it's basically U transpose lambda U. U are the eigenvectors, lambda are the eigenvalues. And this matrix lambda is diagonal. Right? So U is basically just a glorified rotation. Let's look at the document camera. We'll see what happens. Right? This is my Gaussian. This is my covariance matrix corresponding to it. So if these are, you know, say x1 and x2, then, well, the new directions of the covariance would be this one here and that one there. And so basically all that happens over there is, so we say, well, you know, let's just rotate into the eigensystem that's given by U. So I rotate x, I rotate mu. And then within that eigensystem, it's just a Gaussian, you know, one-dimensional Gaussian in each direction. Right? So basically we have a one-dimensional Gaussian here and a one-dimensional Gaussian here. So if I were to plot, you know, let's call this maybe vector v1 and v2, then I'd get, you know, for v1, I'd get something of this form that's reasonably well smeared out. And for v2, get something of this type. So, right. And yet I should line up, but I'm bad at drawing. Okay. This is already centered. Okay, so that's how we get this from. And so then you can see also, and here's another typo because I forgot the determinant of the matrix there, that of course the determinant is the product of the eigenvalues, so we have exactly, you know, lambda 1 up to lambda d. Okay, 2 typos on one slide. Does anybody have questions about this so far? No. All cool? Good. So here's that same picture again. And now I got the normalization right, so lambda I to the minus 1. So, why do you care? Well, the first thing is, as Barnabash already taught you in the past 2 weeks, the central limit theorem gives us, you know, shows us that in the limit all the averages behave like Gaussians. So it's probably a good idea if we have a good handle on it. The other thing is, it's really, really easy to estimate any parameters for a Gaussian. We've all, at some point, computed averages and covariance matrices. So usually, you might have seen this a little bit differently, right? And I'm quickly going to derive what happens. So what you usually would see is something of the following form. Basically, you'd want to compute sum over I, basically xi minus mu transposed xi minus mu. Right? Now xi minus mu x, and of course 1 over m, right? This is what we usually have for the covariance. Now, this, of course, equals 1 over m, sum over I, xi transposed. Okay, so this is the first term that we wanted. Then we get a plus sum over I, xi mu transposed, plus a 1 over m sum over I mu xi transposed. Sorry, the transpose is a 1. And then we have a 1 over m sum over I mu transposed. And we actually have a minus here and we have another minus there. Why didn't anybody notice? Guys, I make mistakes. Sometimes I make them on purpose and sometimes I just make them, right? So, now, does anybody know what these terms are? I mean, I know my handwriting's awful, but this is basically, well, what is it? Mu transposed, right? This is also mu transposed. And so we have minus 2 mu transposed plus mu transposed, which gives us exactly what we wanted, 1 over m, sum over I, xi transposed, minus mu transposed. That's how you get there. This is also useful because, well, the first thing now is an average, right? And the second thing is also an average, so all I have to do is just, compute 2 averages, and then do some slightly non-trivial math with those 2 averages, and I'm done. This actually will turn out to be a really profound property of exponential families. So in all exponential families, as it'll turn out, you can do your estimation by just computing a lot of averages and then happily live ever after. So I remember when I got my first electronic calculator, and I mean, I didn't know much math at the time, but it had this nice variance or covariance function in it, and you could just, it has a statistics mode, and you just add those things. And I was always mystified how you could actually get from there just by taking averages. And so actually, if you expand it, of course, it's really easy, and that's what happens with any exponential family. So you'll see that the same trick works for Poisson, for multinomials, for Dirichlet, and so on. So it's very pervasive. Okay. So this is why it's really easy. On top of that, it's actually also the distribution with the largest uncertainty for a given mean and covariance. Again, this is a property that holds for an exponential family model. So what we might see on Wednesday, depending on how time goes, is that exponential families are actually the solution of a variational problem of finding a distribution with the largest entropy that matches empirical observations. If we don't get to the proof, don't worry, but you can still remember that property. So in other words, if you really have no idea about what the distribution should look like and you just have means and covariances, hey, a Gaussian is not too bad. And it actually works pretty well in practice, even if things are slightly wrong. So here's pseudocode for how to estimate the parameters in case, well, you've never seen MATLAB before, right? And in C it wouldn't be too different. I mean, you would probably want to use something like eigen. So don't code up your own linear algebra library. A couple of solvers that you want to use. The other one is Flint's. Flint's has the probably more beautiful API, but this has a much larger user community. So use this. So never ever code up your own linear algebra if you can avoid it. Because almost certainly these packages will make your code much more readable. And on top of that, it'll be way faster. Because there are people who do nothing else but just tune linear algebra libraries. I'm not quite sure who those people are, but they spend a lot of time on it, so there's tens of man years on it. And they go crazy about allocating memory onto different caches on your processor. You just don't want to do it yourself. If you have a Mac, this is actually part of the Accelerate framework. The Intel Performance Library has it, and AMD has a similar system, so you really don't want to do it yourself. Okay, good. Now, how do we actually sample from a Gaussian? Right? So has anybody tried that before, to sample from a Gaussian? Who has done that before? Okay, actually that's not that many. Have you ever invoked rand_in in MATLAB? Who's done that? Okay, so you have sampled from a Gaussian. Cool. So what rand_in does, so first of all, what does rand do? Well, rand gives you a random number in the range between 0 and 1. Just uniformly distributed, as good as MATLAB or whatever else permits. And there's some C or C++ random number generators that don't go from 0 to 1, but give you a uniform distribution over all the integers. But we also know how to turn that into this by just dividing by that integer range. So this is easy. Now but random number generators for normal distributions aren't quite that easy, right? Because that's really what you want, right? You want something that's straight up. So the first thing is, if I give you a sample from this random number generator, well, how can we make it one that has an arbitrary covariance matrix and an arbitrary mean? Well, the arbitrary mean is really easy, right? You just add it to it and the problem's solved. Okay. For the covariance matrix, well, I'm going to show you that it works by giving a construction and then proving that it's actually the right thing. So what I'm going to do is I'm going to take x is mu plus Lz. This is a useful operation to remember anyway. So we have z being some random variable, which in this case is normally distributed with 0 mean and unit variance. And I'm picking L to be the factorization of that covariance matrix. So it's LL transposed. Does anybody know how I can get this factorization cheaply? Cholesky, exactly. So never code it up yourself, always use Cholesky, right? And there are nice solvers for that. So for instance, if you use the BLAST library, which sits underneath these two, you might get a function call that looks as follows: SPOTR. Symmetric, single precision, positive, or basically positive, semi-definite, triangular factorization. That's what this stands for. Now you'd wonder why it's such a cryptic, bizarre function call. Well, thank Fortran for that. Basically, they had a length limit on the number of characters for a function name, and so they came up with this reasonably object-oriented system of characterizing things. So the first character is single, double, complex, and double complex. This is the matrix type. This is what it does, basically, so triangular factorization. So the solver for that then afterwards would not have an if but an is. This is exactly why you don't want to use BLAST, but you want to use one of those two. Okay, good. Anyway, so we have this thing, so we have LL transposed. Well, in that case, let's just compute the covariance, right? So we take the we all agree that if Z has zero mean, that LZ also has zero mean, right? I don't think I need to prove that. But, so let's take the expected value of x minus mu times x minus mu transpose. Well, that's basically, let's plug things in. So it's LZ, and then Z transpose, L transpose. Okay. Why am I allowed to switch the expectations here? Does anybody have a suggestion? Why may I do this? Yes. So basically, expectations of a linear function mean that I can take the linear function of the expectations. That's the reason. So in other words, if I have the expected value of AX, and A is a scalar, then this is, as we all know, A times the expected value of X. Okay. Now, what we have over there looks a lot more intimidating than AX, right? But it's the same thing. So it's the same math going on, it's just that you have a quadratic number of terms. But that's the beauty of writing things in matrix notation, that you don't really have to look at all those quadratic number of terms. Okay, so that's why I can pull these matrices out of the expectation. And then, well, once I have this, I know what the expected value of Z transposed is, because that's just the unit matrix. That's the identity matrix. That's how I constructed it. So we have LL transpose, and lo and behold, that's exactly what we plugged in. Okay? So, this is how you can color a Gaussian. And if you have a random number generator that gives you Gaussians, that's all you'll ever need to remember. Now, let's say we want to make a Gaussian from scratch, right? So how would you do that? So one way of, getting that is, of course, to use the, cumulative distribution function. Right? So, but don't do it this way because it's just super expensive, and but in some cases that's about the only thing that you can do. Let's say I have some distribution, x is drawn from some p of x. And let's say this is, x is in R. Then what I can do is I can just compute the cumulative distribution function. F of x is the integral from minus infinity up to x of basically dp of, let's say. Okay, now, if I do that, then I know that f of x is going to take on values exactly between, what values does f take? 0 and 1, exactly. Good. And, well then, we have this. Transform into here. Here's 1. I go and draw a random value here. I slice it, and then I just see where this cut occurs, and this is the number that I'm going to pick. And that, of course, so all I'm doing is I'm just putting things upside down here like so, will give me a distribution over these values that matches exactly that distribution. You can work that out. Basically, all you do is you take the derivative of f of x, which gives you p back, and that's the proof. So, unfortunately, as we all know, for a Gaussian, the integral is nasty. So, that's exactly, if you use ERF or ERF-C, working that out is not pleasant. And, well, since Mr. Gauss didn't have a computer, you might also wonder, how on earth did he compute the normalization? And there's this really beautiful trick called the Box-Muller transform. So let's just write up p of x in 2 dimensions. right? That's just 1 over 2 pi e to the minus 1/2 length of x squared. Because we have x1 squared plus x2 squared. Okay. So now I can go and reparameterize things in radial coefficients. So what I get is this expression here. So it doesn't really depend on phi, and radially, and oops, I made a mistake, there should be an r here. Right, so, this is bad, yeah. I have too many typos today. So, what really should happen is that P of r and phi is 1 over 2 pi times r times e to the minus 1/2 r squared. This is just by going from x1 and x2 to r and phi. And of course I know that x1, and we'll need that actually afterwards, is r times, in this case, well, cosine phi, and x2 is r times sine phi. Remember those equations because we'll see them afterwards. So what really happens is this here. We parameterize things in terms of radial part and longitudinal part. And in this case, well, since it nicely factorizes in r and phi, more specifically, it doesn't really depend on phi, the density, well, we know that, spherical Gaussian is rotation invariant, so I can turn it around, it gives me the same thing. I can first of all go and draw from the radial part, so the angular part. So I do this, right? So I basically draw a random number between 0 and 1, and I multiply it by 2 pi, so this gives me an angle. Easy. Now for the radial part, I actually have a rather beautiful looking integral. I have this part here. And as you can easily see, the integral from minus infinity to r, capital R, of r times e to the minus 1/2 r squared, dr, is nothing else but e to the minus 1/2 r squared evaluated between minus infinity and r. Yeah, minus here. Okay. So now, the nice thing is that, okay, so here's the CDF. And, well, rather nicely, you'll see that, well, this is now good. This is something I can easily evaluate. More to the point, I can also invert this. That's what happens here. So solving this first part, 1 minus e to the minus 1/2 r squared is, some random variable z. So I get that e to the minus 1/2 r squared is z minus 1 minus z. So taking the log of that, and then minus 1/2, so we have basically r squared is 2 minus 2 log of 1 minus z. So we get that r is square root of minus 2 log 1 minus z. So, now if you look at the pseudocode, that's almost what's written there, except that I've, say, temp 1, temp 2. Temp 2 is basically the angular part, temp 1 is the radial part. So the only thing is I'm using temp 1 rather than 1 minus temp 1. Why am I allowed to do this? It's a uniform random number, and if I mirror it, it gives me the same thing. So that's all you need to know in order to make two Gaussians out of two uniform random numbers. So the slight inconvenience is you can't just, draw one, but that's not a big deal. There's a couple of other transforms that are in some cases faster if you just need one at a time. So there's something called a cigarette transform. And basically, again, this is an entire industry. You don't want to do this if you can avoid it. So, link against the statistics library, import a statistics package, whatever. Try not to doing that work yourself, because almost certainly you'll do it worse than what's in the library. At least I try not to make those mistakes myself. Now, okay, so here's something very simple. We have height and weight. We'll actually get back to this in a moment. And let's say we want to correlate this. So let's say we take a Gaussian correlation. So now we can actually bring our tools to bear, right? We can go and estimate the mean and covariance of height and weight. And yeah, these are European measures, right? Because people aren't quite 180 inches tall. Sorry, but yeah, I'm still metric. But if you do that, then, well, you can do something fairly straightforward. You can ask questions like, what's the expected weight given the height of a person? Or vice versa. So that's the kind of thing that the doctor would do if you go to, maybe you've been eating too much and he wants to figure out whether you should go on a diet. Well, he'll look at the chart, figure out, what the average value is. And if you're above it, well, okay, tough luck. So here's what we do by Bayes' rule, right? This is basically just, P of height and weight divided by P of height. Now, height in this case is a constant, so I'm conditioning on it. So therefore, I know it's proportional to the joint between height and weight, but I just don't change this. Okay, this looks like a very stupid, simple thing to do, but it actually simplifies things a lot. Here's why. So remember, here we have two variables, x1 and x2. I've just not written height and weight, so it's the same math. And here I've just written out everything, basically the entire covariance matrix and everything just in coordinates. So I know this equation looks hairy, right? So it has, well, 8 Greek symbols in it, and altogether it has something like, 14 variables and then an exponential, oh my god, but it's really not that complicated. Right. Inverse covariance matrix, observations minus their means, same thing here. Now, here's the cool thing. This is a trick that I learned from Chris Bishop. Basically, if you squint at this really hard, you can see that, well, it's going to have linear and quadratic terms in x2. Well, the normalization is already screwed up anyway, so, well, whatever. Now, all I need to do is I just need to pull out the linear and quadratic terms in x2, throw away the rest, but that tells me enough to tell me what the mean and covariance is in terms of x2. Okay. Let's actually go through that math in a little bit more detail, and then afterwards I'll show you the solution. So let's say we have, just some variable p of x is proportional to e to the minus 1/2 ax squared plus bx. Right? So this is, just a quadratic function in x. So can we work out the mean and covariance? Well, all we have to do is now we just go and complete the square, right? So I can write 1/2 1/2a, and now here we have x minus, the sign's already nicely flipped, minus a times b. That cancels out quite cleanly. And now, just square this. And then we need to correct for that. And a minus here. So we added it, so we subtract it again. So we get a minus 1 over a times a here, right? A squared. B squared. Okay, so we have a minus b squared over 2a. What?
It's not totally perfect here.
Well, we need the normalization up here with the 2 pi's and all that.
Because you had a times x squared, and now we have x squared over a.
Yeah, because now it's correct. Okay. Yeah, that's something that's easier on paper. But what you can see from that now is that, the covariance is simply, sigma squared is A. And furthermore, we have that mu is A times B. And if you had A in the numerator, then, you just flip that. So, thanks. Guys, you should have told me that earlier. I mean, why is Barnabas the only guy telling me that I screwed up? I mean, okay. Oh, I'm not sure. Because you're adding. Okay, it doesn't really matter because all we care about is really just this quadratic part, and then you normalize it. But basically that's the entire trick. You pull out the linear quadratic terms in x, you complete the square, and that's it. Okay. Now, this was reasonably straightforward. There's still enough potential to screw up. Now let's do that for here. So this is the thing that you will want to do once in your life and probably never again, to explicitly write out the inverse of a 2x2 block matrix. Have you ever done this before? Probably not. Okay, so there's one guy, okay, 2, 3, 4, wow, okay. So on a nice Sunday afternoon when you have nothing else to do, you should do that once, and you'll remember that Sunday afternoon. If you don't, get your hands on this book. It's ridiculously expensive, but it's a really nice book, which contains everything you never wanted to know about matrices. Yeah. So if you pull up this book, and then you just check, what comes out for this, the only term we are really interested in, right? If you recall, is just, this x2 guy. So we only care really about that lower right entry here. And then the cross terms. So you just look them up. And here's the first thing. So for k, so that lower right triangle, block, is just ktt prime minus now kt t prime transpose ktt inverse ktt prime. Okay, so you can check that if you want. And this is what you get for the mean. Okay. Now, well, why do I care? And yeah, this is the kind of stuff that you actually should remember at least where to look it up. So, first of all, this thing here is a covariance matrix. It's kind of nice. So why is it a covariance matrix? Well, we had a Gaussian before. We know that, condition on one variable, the rest is still a Gaussian. So since Gaussians cannot have negative variance, we know that this is still a positive semi-definite matrix. It might have covariance 0 if, the t's completely determine the t primes, but that's about the only thing. Can never have negative spectrum. Which is kind of cool because, you're taking this thing, you're subtracting something from it, and it still works. Who has worked with a Koleski decomposition at some point? Okay, cool. So if you looked at the code of the Cholesky decomposition, it does actually a deflation step which does exactly this. You basically pick one entry at a time, you compute a new factor, basically a new vector, and then you deflate the matrix that you had by this. This is exactly what's going on. So in that case, these guys here are one-dimensional. They're just scalars, and these are vectors. And then you just keep on adding things to it. So the other nice thing that you can see is here that the covariance is reduced, but it's reduced commensurate to how strongly correlated t and t primes are. If these variables are very strongly correlated, they get a massive reduction. This is exactly what I would expect. If they're strongly correlated, then knowing one thing tells me a lot about the other. So for instance, if height and weight were very strongly correlated, then just knowing the height immediately tells me the weight. The other thing is, it's inversely correlated to the variance in the t's. So that means if the variable that I'm trying to predict, that I'm using for prediction, is super noisy, so if it's very uncertain, then of course, having a strong correlation doesn't help me so much. So that actually goes exactly the way you would expect it to go. And now, for the means, we get a similar thing. So we basically get that it's the original mean that we would have thought that, t prime would take. But now again, I have this correlation. So if two variables are strongly correlated, knowing one will tell me a lot about the other one. That's exactly what I have here. And then again, if the variable that I'm using to make any inference with is very noisy, then maybe it's not going to be so valuable. And all of this is tempered by just how much the actual observation of t deviated from what I would have thought it is. Okay. This is actually all the math that you'll need to know to do Gaussian process regression afterwards. So that's why I'm going to this slide in a lot of detail. Okay. If you understand this equation, you can do Gaussian Markov random fields, you can do Gaussian process regression. It's then afterwards really just going to be an exercise of plugging different interpretations in for k and mu. Okay. Questions about this slide? I can talk longer about it, so if you have questions, ask now. No question? Everything clear? Okay. So here's the normal distribution again. So this is just a small summary of what we went through so far. Well, we've all seen the normal distribution. To draw from it, well, you use this very simple construction, mu plus Lz, where L is the Cholesky factor. You can always work that out yourself by just checking. I mean, this is actually how I worked it out for the slides. I always get the transposes wrong otherwise. So you just figure out what it's supposed to be, and you plug it in here. Just one thing to remember, this goes with the inverse covariance matrix, and this goes with the covariance matrix. Okay. Then estimating the means and variances is fairly straightforward. We went through this. And then this conditional distribution is also Gaussian. You can just check that by looking at the linear and quadratic terms. Okay. Good. So now let's actually put that to good use. So far, this was really just a warm-up to get ourselves familiar with Gaussians. Okay. Now it's gonna get a little bit more theoretical. So the key idea is the following. So suppose that with height and weight we had essentially two random variables, right? So we have some index set. But now, I can make this index set as large as I want. I could, for instance, take the average homework scores of all the students here. And I define maybe a normal distribution over all those homeworks. You would think that, there's going to be some sort of a correlation because, if the problem is really hard, then a lot of people are not going to get it right. If it's really easy, a lot of people will. And then maybe there are some anti-correlations. Maybe somebody is really good at coding and somebody else is maybe much better at proving theorems. So then, now you would see some numbers there. So I can, define a normal distribution on the homework scores of everybody. I can do that by, just making that a function, right? And if some new student comes along, I can, go and, complete that matrix. I haven't told you how I actually cook up that covariance matrix, but assuming that I could do this, well, we'd be in business. Now, a stochastic process does exactly that. It basically says, well, suppose I have a distribution over, random, so I have some random variables, and instead of, having this finite dimensional vector, I now have an infinite dimensional beast, possibly infinite dimensional. And I'm going to go and evaluate it at some locations xi, so there's some index set, and I'm going to, observe some random variable. So I'm going to observe some t of x. So think of this like, you have a function in your code, and you give it an argument, and it comes back with a number, with a random number. It might come back with the same random number depending on how you set it up, but basically, for each argument, it's going to do something. And if you don't pre-specify, the space of your arguments, you have a stochastic process. Now, the interesting thing is that for a Gaussian process, all I need to know is just the means and covariances. So it's defined as follows, that if you evaluate this Gaussian process on d locations, you get d-dimensional vector, and no matter at which locations you evaluated it, it behaves like a normal distribution with a given mean and covariance. That's the idea of a Gaussian process. And so therefore, all I just need to be able to do in order to fully specify this, well, I need to specify the mean, mu of x. I need to specify the covariance function k of x and x prime, which is the covariance of t of x and t of x prime. So this might already give you some hint that these are actually going to be our kernels again. So I'm not just overloading notations. This is the same covariance function, the same kernel that we used before when we did support vector machines. And I'll show you next, so on this Wednesday, how they are closely related. So there's a one-to-one mapping actually. So the key point is that, as soon as I have this covariance function k, then, I'm done. The other horrible assumption that people usually make is that they say, well, mu equals 0. Do not do this in practice for a specific engineering solution. So do not do this in practice. Like for instance, if you're measuring, I don't know, maybe voltages, right? And it's typically 110 volts. Well, setting mu equals 0 is an idiotic assumption. So let's say you want to measure the voltage fluctuations in a building, an electrical engineer, and you want to model that somehow. Setting mu equals 0 and then building a Gaussian process is the most stupid thing you could do. Do not do that. It will not work as well as if you actually use your brains and solve the problem at hand. Okay. But I'm going to make the simplifying assumption just to make the equations look less intimidating. That's the only reason. Okay. Does anybody have questions about Gaussian processes so far? Because this is a fairly abstract concept, right? So we have basically now not d-dimensional vectors, but now we have essentially a function. So basically you could think of it just like a function, and whenever you evaluate it, you get another random number out of it. And these functions might have interesting properties. So, questions?
So,
yep.
In the practical scenario, you can just subtract the mean and process like you have, like,
that's
PCA, you subtract exactly.
That's exactly what you would do. You would basically subtract the mean, and then you happily move on. And if you have, except that in this case, well, you would have a mean function. Right? So this mean function might be, for instance, your guesstimate, or maybe you join a project and some engineer has already hand-coded a lot of things. Then you take his hand-coded solution and use that as mu. This is actually a really useful trick to remember when you later on get a job. Basically, quite often you'll be pulled into a project and somebody has already done a good job at hand engineering and handcrafting things. And your first intuition is, well, hey, this is all really horrible, it's so hacky, I hate it, let's throw it out. Then you use your own fancy technique, and the net result will often be that it doesn't work as well as the hand-coded solution. And so here's why. Because this guy had, or this girl, had years of time to handcraft and tune and very, very specifically fine-tune the solution. So it's complete arrogance to assume that you can just walk in. I mean, in some cases you can, but if the engineer was good, you can't. And within a day or two, blow him out of the water. Okay, so here's what you do. Extend and embrace. You basically take his handcrafted solution, use it as mu, and then you say, well, okay, now we're going to make a model that builds upon this and extends. It does two things. First of all, it works better. Secondly, it makes the guy happy. And so you'll have a much higher chance of actually getting this accepted. So remember that trick. Means are really useful in that case. Okay, so here's an example for a draw from a Gaussian process. So I pick some point where I want to sample. I go and compute this covariance matrix. And then I draw as if it were from a Gaussian, in this case from 7 dimensions. Right? So the important thing is this is actually only giving me the values at those points. So drawing a line between that might look sort of kind of reasonable, but it really isn't. So there are processes where whatever I get out of it is not smooth. So whenever people draw curves, and I'll be doing that too for a Gaussian process, keep in mind that this is only for looking at a lot of points and then drawing from it. So it's not quite the same. So here are some more draws from a Gaussian process, and they look as squiggly as they would. All right. But what this already tells us is that those Gaussian processes, if I just pick the right covariance function, can be really useful tools at parameterizing smooth functions. That's the main reason why they are so popular. As a matter of fact, we did smooth functions 2 weeks ago when we did support vector regression. Turns out this parameterizes essentially the same smooth functions. Yes, there are some mathematical details that I'm not going to go into, but basically the same criteria that tell us whether a kernel is going to give us something useful will tell us the same answer here. So again, sampling from a Gaussian process. There's this thing here. Well, you compute the covariance function, and then there you go. So now, as already hinted at, so kernels. In this case, we have this covariance function, takes 2 arguments, it gives us matrices, they have no negative eigenvalues, and this describes this correlation between pairs and observations, right? This is the covariance function. For a kernel, it also takes 2 arguments, it also gives us a matrix with no negative eigenvalues, gives a similarity measure. So if you squint at it hard enough, you think, this looks very similar, and as a matter of fact, they are the same. And the surprising fact in hindsight is that it took about 8 years until Chris Williams wrote a paper and said, here's the proof why they are the same. And once you see the math, you'll really think that it's very surprising that it took 8 years. Because it's basically just, you take linear functions and you parameterize them in the right way. And we'll get to that, but probably not today. So, small summary. What I really want you to remember for a Gaussian process is, well, just think of distributions over function values, not the entire functions. You're not really drawing from the function space, because this function space may be infinite dimensional, and all sorts of math may go horribly wrong, because if you have infinite dimensional spaces, then if you don't normalize it in the right way, your integrals diverge, so this is not fun. You can write entire books about that, and definitely beyond the scope of this class. But then, if for pointwise evaluations, that's fairly straightforward. You just get the mean and covariance function, and you generate from that. Okay. Now let's do something actually useful with it, Gaussian process regression. Okay. So apologies for the scary math, but this is a conceptual tool that you need to have some intuition about. So let's go back to height and weight. Right? So, as I now convinced you, this is actually a Gaussian process, right? It's a Gaussian process over what domain? Can somebody tell me what the domain is for it? Does somebody know what the domain for the Gaussian process is that models the distribution over height and weight?
All the points of people.
Almost. So it's actually a lot simpler than that. The domain is just the index variable height and the variable weight, not even the identities, because these. And now, so it's a so it's basically a function or in this case a process that you can evaluate on 2 points, right? Height and weight. If you could have one that goes over height, weight, and age, but maybe modeling age with a Gaussian is not a good idea because we can't really have negative ages, right? So in some cases Gaussians aren't such a brilliant idea, but in that case it would be indexed by 3 variables, height, weight, and age. And now over those, for those 3 terms, you would, draw numbers, height, weight, and an age. And then you would have basically, a 3-dimensional Gaussian. So, and what we want to do is in this case, in this 2-dimensional Gaussian process, we want to infer weight given height. We basically want to regress from the height on the weight. After all, that's what regression is, right? You observe some things, you want to infer the other parts, right? Now, here comes our Gaussian again. And the idea now is basically, we go and observe those t's. We want to infer the t primes. So the t's might be, function values at a couple of locations, and the t primes might be function values at a couple of others. Or the t's might be, height and weight, and then maybe the t primes might be the age, or maybe the cholesterol level, right? Stuff like that. And so as soon as I give you the covariance function and the means, I'm done. Now, I haven't told you how to get this. In some cases, you basically pull it right out of thin air. In some cases, you can actually, do some measurements and log stuff and so on. But basically, if somebody gives you k and mu, then you're home, right? Because now all we do is we just, work the algebra here. This is exactly why I went with you through this stuff in fairly excruciating detail. And here's the mean. So these equations look familiar. Now, the only nice thing that you might want to do is you might want to actually do a little bit of pre-computation. First of all, you probably want to pre-compute this yellow part here, such that if I get a new t prime, then I can just plug in another matrix here and I immediately get the solution. Because, okay, so by the way, can somebody tell me how expensive computing this is in terms of sample size? Is it linear, quadratic, cubic, quartic? So who opts for linear? Who opts for quadratic? Who opts for cubic? Who opts for quartic? Okay, and the rest is asleep. It's cubic, yes. Okay. Now, if I pre-compute the yellow part, how expensive is it then? Is it linear? Is it quadratic? Is it cubic? Okay. Nobody's quite so sure, right? Guys, you gotta have some idea. Okay, so if I compute this, right, this is a vector, that's a vector. Vector times matrix inverse, okay, so if I pre-compute it, I get a vector out of it. So this becomes a matrix vector operation. So, what is it now? Linear, quadratic, or cubic? Quadratic, right. So, basically, after I do the hard work for the yellow part, doing the rest here is quadratic. So, it's a lot faster. In many cases, quadratic is still too expensive. And there are actually a whole bunch of tricks on how to make this a lot cheaper. But this is quite advanced material. So if you come to Geoff Gordon's group meeting tomorrow, I'll actually be talking about how to make a lot of this linear. But yeah, this is fairly advanced material, so don't worry about it for the moment. So what you can see is at least you can make this a lot faster, and now it only depends on the number of points that I want to evaluate it on, and the number of points that I used for training. Now, this covariance matrix is a little bit messier to see how you can speed things up. Does anybody have an idea how to accelerate this? So first of all, what's the dominant cost? Is it the first or the second term? Who opts for the first term? Who opts for the second term? Good. You got it right. It looks messier as well. Now, the expensive part in here is actually this matrix inverse, right? So an obvious thing is, it's the same matrix inverse, so maybe we can recycle some work. If I do it naively, well, what you can see is that this is actually cubic, right? Well, we multiply three matrices, and each of the matrix products is cubic, so that's no good. However, okay, does anybody have a suggestion of how we could accelerate this? Cholesky factorization. Exactly. That's exactly the tools that we did before. And so what you do is, right, so you have basically one matrix here. You have this KTT inverse, and you have another matrix here. And so the idea is to use the factorization, LL transpose. And the cool thing is that I can now compute this product, which is the same as this product here. And so now I just compute this one matrix product and then multiply it with itself. The only thing is we actually had L inverse. Would you ever go and compute L inverse? No. Why wouldn't you want to compute L inverse? Because? Any suggestions? Exactly. So if I ever computed L inverse, this will give me another dense matrix again. So this messes everything up. So you don't want to do this. However, if I have a lower triangular matrix, then solving a linear system of equations with that is actually fairly fast. It's faster, and it's also numerically more stable to explicitly solve the system rather than compute the inverse and then multiply by it. If this type of linear algebra reasoning is scary for you, you should pick up an Introduction to Numerical Linear Algebra book. This is something you'll benefit from, not just for this class, but in general. Okay, so who thinks this stuff is scary? Because if there's a lot of votes for that, we can have a tutorial on it. Okay, so who thinks it's a little bit scary? Who thinks it's very scary? Okay, who thinks it's not scary at all? Wow, a couple of brave souls. It's good. So I think this probably warrants a little bit of background in one of the tutorials. Okay. So basically, you pre-compute this, and you can use the same matrix that you have here, also for the yellow bit on the right. Actually, if you squint at it, you realize that it's basically L inverse T minus mu, and then the other L inverse is applied to KTT prime. So you basically, these are the two parts that you need to compute, and then you're done. As in, if you have to compute this anyway, why not do that and then just run the rest? If you didn't, then you'd first invert with one factor, then with the other. Okay, good. Now, here's what's really nice about it. The predictive uncertainty is data independent. So this is really good for experimental design. And there's a very nice paper by Klaus Gestrin and Andreas Krause from 2005, where they actually use this to, for instance, design chair sensors, or to determine where to place sensors in a lake. So chair sensors to infer, whether your posture is okay or not. And it turns out that a symmetric design is not the optimal thing, which is quite obvious, because if you're leaning to one side, you can't at the same point be leaning to the other side. And their active learning algorithm actually gives you that straightforwardly. The bad thing is that the predictive uncertainty is data independent. So yeah, it's a good and a bad thing. So why is it a bad thing that the predictive uncertainty is data independent? Does anybody have a suggestion? Are there any cases where you would not assume that the predictive uncertainty is data independent? Actually, in most cases of life, it's not data independent. It's like you build a system, and the Gaussian process, in a way, is so supremely confident in its own abilities that even before testing it out, it can already say, well, hey, this is how certain or uncertain I am about what I'm going to see. So you would almost certainly not be so crazy to, claim that you don't even need to see any data before you know how well you're doing. This is like saying, hey, I'm going to get, an A star in this class before even taking it. Well, maybe you can be that confident, but I think it probably helps to, do the first few homeworks and see how you're doing to find out whether, you get an A star. Okay, so this is why it's not good. Now, there are ways around it. So the most obvious thing is you can say, well, hey, actually this covariance function k, maybe I didn't quite know it so well, so I can actually try to infer it. The much more immediate thing is, I might actually assume that what I'm observing is not exactly drawn from that model, but somehow corrupted, and then I play with the corruption. And we'll be looking at that, well, to some extent today, and then a lot more on Wednesday. So let's just do, linear Gaussian process regression, and that already shows you where this predictive uncertainty part can go a little bit wrong. So, let's take a linear kernel. After all, it's a kernel. It gives us a covariance matrix. So here's what we get, right? K tilde is, this was exactly our Schur complement from before. Let's just plug it in. Now, if you squint at that, you can see that this is basically the projection operator onto the space spanned by x. So in other words, you have x prime transposed 1 minus the projection operator on x, x prime. So if you have d-dimensional data, and you have more than d observations, then you get in trouble, because this here becomes the identity matrix, at least unless the data has some pathological distribution to it. So in other words, the predictive uncertainty is 0. That's like saying, well, give me d observations and I can perfectly tell you the rest of the world, which is obviously wrong. In the mean, okay, this is very straightforward. We have a linear regression here. So, well, what went wrong? Well, the bad thing is that this covariance matrix, of course, has at most rank in dimensions. And after these, the variance vanishes. So we have that kind of a distribution. I mean, actually, you'd have to squish it a little bit more flat, but if you were to tilt, you look at it from the side this way, you see it's flat. Okay. So basically, what we did is we underestimated the uncertainty because we made a very, very simplistic and wrong assumption. So here's what we did, right? We assume that we have some data, x. This is what indexes our stochastic process. Then we have some observations, t, that are drawn from that. So, any suggestions what I could do? And there are basically two strategies, and they actually turn out to be equivalent. At least there are two strategies. Any suggestions? Okay, so the problem is this Gaussian has been put on a diet. We need to fatten it up again. So basically, one way is to just add something to the main diagonal of that covariance matrix, right? Sounds like a completely horrible hack. Actually, it turns out to be exactly the right thing. You've probably done this in the past if you had to solve a linear system of equations, and then maybe MATLAB or whatever said, well, hey, the matrix doesn't have high enough rank, you add a small epsilon to the main diagonal, and then all of a sudden you could invert things and it sort of worked. Who's done this before? Yeah, exactly. Now I'm going to show you why this is a good thing. So here's what we're doing. I'm going to say that actually those t's that are maybe in this low dimensional space aren't really what I'm observing, but maybe my measurement device is a little bit wrong. So I'm not giving up on my assumption that the reality is simple, but I'm just saying, hey, I'm not observing quite the reality, but I'm observing, whatever I should be observing, plus a little bit of noise. Okay. And here's the math that goes with it. I'm assuming that my t's are, as before, drawn from a normal distribution with mean, mu, and covariance matrix K. And then the various yi's are drawn from a normal distribution with, mean ti and covariance sigma squared. Now this should look awfully familiar from your first homework, right? Okay, so if you did the homework, you would already know the answer. Let me just walk you through that. So remember, we have t is drawn from a normal distribution with some mean mu and covariance matrix K. And then we have y drawn from a normal distribution with mean t and covariance matrix sigma squared times the identity. Okay. Now, in that case, well, let's work out what the distribution for the y's is. Well, let's compute the expected value. The expected value of y is the expected value of t plus epsilon, where this epsilon is drawn from a normal distribution with zero mean and unit variance, sigma squared. So this is nothing, since this has zero mean, this goes out. So this is basically mu. Good. Now let's work out the covariance matrix. So the expected value of y minus mu, y minus mu transpose. Now let's plug in what we have for y. We have that this is t plus epsilon. So we have basically the expected value of t transpose plus, actually let me just do the following thing, t minus mu transpose. Then we get plus epsilon transpose, and then we get the cross terms, right? We get basically epsilon times t minus mu transpose plus t minus mu epsilon. Okay. Now, by linearity of the expectation, we can plug things in, right? So we know what the expected value of t minus mu transpose is. Who knows what that is? K, exactly. So this is K plus, what's the expected value of epsilon transpose? Sigma squared identity, yeah? Now, what's the expected value of this term here? 0, exactly. Why is it 0? Because they're independent Gaussians. Exactly, they're independent zero mean random variables, so I can take the expectations over each of the factors separately, so I get 0. And this one is also 0 with the same term root. So, in other words, what we've just done is we've solved an integral without even noticing it. So y is drawn from a normal distribution with mean mu in covariance matrix K plus sigma squared times the identity. And this solves our problem. Right? Because basically now we've made the matrix full rank even though it wasn't before. And then I can just happily go and regress. And we'll do that on Wednesday. So basically just what happens here is exactly what I showed you before. We just went and solved this integral. We integrated out this variable t. We did this by knowing that, for a Gaussian, you only need linear and quadratic terms. And this is what we got. In general, this integral is not so easily solvable. We'll encounter a lot of cases where this will give us a lot of a headache. But today we were lucky. So, any questions? Homework will be out today. It appears that I sent a draft of the homework to the wrong email address. So if you've already started solving it, you probably have a bit of a head start, but the final version today will be correlated with what you saw, but maybe not identical. But you have time until the week thereafter, because there's semester break anyway. So don't worry, you'll have more than 2 weeks' time to solve it. Okay. So I'll be outside, and we can talk for maybe half an hour or so. We've had homework 1, so come pick them up. Homework 1 is ready. Just get it.
Prediction of Indonesia, which means that this is okay. What I have is the giant bit has a bunch of strings in it, which phoneme
Okay.
and a bunch of floats. And I'm thinking we can support vector machines,
Yeah.
but I don't know how to normalize deal with the strings.
How